Yeah, I can hear you. I'm audible, yes?
Yeah. So you have the floor.
All right. I'd like to introduce all you people to Mehmet, who has worked with me for the last 2 months. We covered a surprising amount of homotopy theory before breaking into modern homotopy theory, which is known for being a very difficult field to usually break into. So my congratulations to him for that. And with that, I'll let him tell you about his products.
Hello everyone, today I will be presenting about infinity categories and higher algebra. I will basically give a brief review of infinity category theory, then I will move on to the infinity category of spectra, then I will show the necessities of EM algebras and give a definition of a steenrod operation in the higher categorical language. So for the infinity categories, we need to start with the simplex category, whose objects are linearly ordered sets, and morphisms between the objects are order-preserving functions. A simplicial set is then a functor from the opposite category of the simplex category to the category of sets. Our infinity category is a special type of infinity category where we can define that all compositions exist, but compositions, unlike in a normal ordinary category, are not unique, but they are unique up to contractible choice. I will get to that. And a complex is a special type of infinity category where the addition to composition, we now have every morphisms to are invertible, but again the inverses are defined up to contractible. Informally, as this is a simplicial set, where one can think of each vertex as an object, each edge as a morphism between objects. Those edges one can think as directed. And the higher cells, the two simplices, three simplices, are actually homotopies between the morphisms and homotopies between homotopies of morphisms and so on. This is why they are called infinity. And this, if one thinks this as an infinity category, we have three objects, x, y, and z, and two morphisms, f and g. And in the infinity category, we can extend this diagram via h from x to z, and the homotopy from G composed of F and H. But as I said, this is only unique up to contractible choice, which means that if we even have another homotopy, then those two homotopies are actually homotopic to one another, and those two homotopies are actually homotopic to one another, so on. And all of these choices are actually contractible. And down below, if we think that it is a complex, then one can extend this diagram to via morphism G, such that G composed with F is identity morphism. And this way we introduced the compositions in an infinity category and inverses in a complex. And now that we have defined simplicial sets, complex, and infinity categories, we now define the morphisms between them. But we require the morphisms between them to not just be a standard set. We also require that to be a simplicial set as well. For that, we define the fun CD, which is also a simplicial set whose n simplicities are given by from delta n times c to d. For example, if we just take the n equals to b0, we just get a map from, we just see that the n simplicities are given by home cd, which are the ordinary morphisms between c and d. And when n equals 1, we get an additional delta 1, which is as a straight line. That straight line accounts for the natural transformation between two morphisms, which are the edges of that. It is the vertices of that edge, f and g. And if we restrict ourselves to the category of infinity categories, then fun CD is also an infinity category, as in position 1. And then if we restrict ourselves to the category of complexes, then fun CD is also a complex. And this way, unlike our ordinary category theory, we have enrichment. So like our morphism sets are simplicial sets, infinity categories, and complexes, for example. And we are especially interested in then our category is enriched over Kahn complexes, because we have a functor called homotopy coherent nerve, which maps Kahn-enriched categories to infinity categories. This way, as I've seen in proposition 2, the category of Kahn complexes is enriched over Kahn complexes. Therefore, by applying homotopy coherent nerve, we get the infinity category of Kahn complexes, which I will denote as AN, and it is called anima or spaces. And as we talked about, the infinity categories are enriched over just infinity categories. But if you take the largest Kahn complex inside that fun CD, which is an infinity category, and then apply homotopy coherent nerve, you get the infinity category of infinity categories, which we will denote as cat infinity. So we also have two constructions, suspension and loop space construction. So we take X to be a pointed anima as we defined before. And then the suspension and the loop space are given by push-outs and pullbacks of this diagram. But these are not the ordinary push-outs and pullbacks, because if one is familiar with algebraic topology and category theory, the push-out of the two discrete points is just another discrete point. So we need homotopy push-outs and homotopy pullbacks that are basically push-outs and pullbacks, but they behave well under homotopy. With this definition, we introduced the infinity category of spectra, which is the limit inside the infinity category is cat infinity. As this, we just take the loop space again and again, and we get a sequence between the category of Kahn complex anima, pointed Kahn complex. And taking the limit of this sequence, we get the infinity category of spectra. Unfolding but the definition of a limit, this is nothing but just a sequence of pointed anima, xn, such that the loop space of xn plus 1 is homotopic to xn. And this is a very, very special category. In fact, usually the suspension is adjoint loop space factor, but inside this category, they are just mutual inverses, which everything behaves well. And also we have a functor called infinite loop space functor, that we have like a sequence of objects inside a spectra, and this infinite loop space functor maps this spectra into the first, zeroth object of that spectrum. So we give examples of spectra. This is like the most dominant example of a spectra. So as I said, the loop space and suspension are adjoint functors. So by just taking the nth loop space of X to be the anti-anima of a suspension, of a spectrum, one thinks that, we can take the loop space and we can just get ourselves a spectrum. But this does not work because our X is not stabilized yet. For example, just by taking X to be S1, we can take the suspension of X, which is equal to S2, and calculating the second homotopy group of the loop space of S2, which is equal to the third homotopy group of S2, and this is equal to Z. But unlike Z, the second homotopy group of S1 is equal to 0. So these two constructions are not homotopy. So before doing everything, we need to first stabilize our anima. And we just, for this, we just take the co-limit of the above sequence given by loop space suspension of X, loop space square suspension square of X, and so on. And this eventually stabilizes our X. And this is because the projectile suspension theorem in algebraic topology. And now, with this definition, if you just start the ordinary and pointed anima X, we just define the suspension spectrum like this. We take the stabilization of the n-pole suspension of X. And for example, when X is just S0, which are two points, basically, one gets the sphere spectrum using this suspension spectrum. And this sphere spectrum is very, very important because, for example, just taking homotopy groups of the sphere spectrum, one gets the stable homotopy groups of spheres plus for free, which are like the main objects of the same homotopy. And SP has, as I said, very good properties. The first one is that it is a symmetric monoidal first of all, it's a symmetric monoidal category by a tensor product. And the sphere spectrum is actually the unit of this symmetric monoidal structure. And we also have these relations, but this structure is not, it does not give SP just a symmetric monoidal structure. It gives it a symmetric monoidal infinity category structure, which is a symmetric monoidal structure that also has all these coherent diagrams and coherence. It is equivalence up to coherency and so forth. And also SP has all of its limits and colimits, and SP is stable, which means that if we take a commutative square, and if it's a push out, then it's a pullback, and if it's a pullback square, then it's a push out square. And also it means that it has a zero object, and also additionally it has finite limits and colimits, but SP has all of its limits and colimits. So. Now we move on to EN algebras, but first I will give the definition of associative algebra and commutative algebra in an ordinary category theory. For this, we need to define SOC and COM, which are two categories. The SOC is defined as a category whose objects are finite set and morphisms are in absolute finite sets, such that the fibers of the images have a total order in them. And we can actually define composition by taking the fibers of the composition to have a lexicographical order. And the symmetric monoidal structure on this is given by the disjoint union, and the unit is given by the empty set. Again, COM looks like an interesting category, but it's just a category of finite sets. And the symmetric monoidal structure is given by the disjoint union and the empty set. And in an ordinary category theory, C to be a symmetric monoidal category, associative algebra over C is a functor A from S up to C. And the category of all associative algebras over C, we will denote it as algebra of C, is ASOC to C. And similarly, if we replace ASOC with COM, we get the category of commutative algebras and commutative algebra over C. And what about associative algebra over the associative algebras of C? And this gives us the commutative algebras over C, because the Ekman-Hilton argument states that if we have two monoidal operations on a set, then if one of the monoidal operations is the homomorphism of another, then these two monoidal operations are actually the same, and it commutes through the another. But things are different in cat infinity, in the infinity category fairyland. So if you take C to be a symmetric monoidal infinity category, then similarly you can define an associative algebra A over C. We have some monoidal functor from, not this time from S up to C, but from nerve of S up to C. Nerve is a way to convert by taking a non-standard category and converting it to an infinity category, which has its n simplices are uncomposable morphisms. And we take algebra of C to be all the strong monoidal functors over C, which will denote as E1. So in the ordinary land, we have used Ekman-Hilton as algebra of C as C algebra of C, but this time it does not work like that. We have E2 as algebra of C and algebra of C as E3, and there is an underlying functor from algebra of C to C just by forgetting the monoidal structure on C, and this gives us a sequence from the below. And taking the limit of this sequence, we get E infinity, which is actually the commutative algebras over C. And with EN algebras, we have a very important principle called Mayer combination principle, which says that for pointed Kahn complexes, these are equivalent. Group like E1 spaces and pointed spaces, which is given by two functors, one given by loop space and the other one is the bar construction. For the loop space part, loop space shifts the homotopic groups by one, so pi 0 of a space becomes a pi 1 of the space, which is a group, so it becomes a group like. And E1 structure is given by composition of loops. And again, similarly, the same thing works for EN algebras. And if we take this to the infinity, we have a relation between group by E infinity spaces and connected spectra, which are spectrums such that their homotopy groups of negative degree vanish. And we actually can define rings and modules in higher algebra as well. So in the ordinary theory of rings and modules, the category of commutative rings is all the monoidal functors from come to the category of abelian groups, as we defined previously. And we have a lemma which states this. I just included this lemma and this to see how similar their definitions are, basically. But this definition is important. E infinity ring is an E infinity algebra over the category of spectra. So, in the sense that if you look, we have C rings are found from AB, all the monoidal functors from COM to abelian groups, and we have again all the strong monoidal functors from nerve COM to SP spectra. So, in some sense, spectra is the higher categorical version of the category of abelian groups. And in a very similar sense, we can also define the modules of those. So we now begin with now go to steenrod operation. But first, we need to know what homotopy invariants and co-invariants are. In the ordinary world, if a group G acts on a topological space X, we can express this as a functor from G to top, where G is a category with one object, and morphism says it's group, and where F, our functor, maps that one object to X, and the invariants and co-invariants are given by limits and colimits. And similarly, in the infinity category theory, if a group G acts on X in a infinity category C, then we can express this as the bar construction of a map from the bar construction of G to C, such that the bar construction is basically like it contains all of the compositions of maps as well. So it's a higher version of considering G as a ordinary category. And we can define its homotopy co-invariants as the homotopy limit and homotopy colimits. And we have a very interesting fact, which says that the homotopy groups of the homotopy co-invariants are actually the homology groups, group homologies of G and the singular group homology of BG, is the classifying space of G. And which will this will come in handy if you replace G with sigma 2, which is symmetric group with two elements, and M to be M with F2. Then the homotopy groups of this is the same as the singular homology of RP infinity in the coefficients in F2, and this is nothing but a generator in every single dimension, which will be known as F2. The generator is E0. And if you take a field K and a V as K module, sorry, V to be a K module, then there's an obvious multiplication given by the tensor product on spectra, given by V tensor V to V, given by M. And V has a symmetric multiplication if this map factors through the homotopy co-invariants of sigma 2. And now we construct steenrod operations. For this, we need to know this lemma as a fact. Now we take X to be now again take V to be a K module such that V has a symmetric multiplication. And we take X to be an element of pi n of V. And this giving the element of pi n of V is equivalent to giving a map from the n-fold suspension of F2 to V. And this map induces a map, just taking this tensor and again the homotopy co-invariants, induces a map called sim squared of X. Then we can, for I greater or equal to n, we can just take the generator of RP infinity of the homology groups of the RP infinity, EI minus n, and take the 2n-fold suspension of that. to be a map from Sn plus 1 to that. And like by the above lemma, this is equal to this. And after taking the sim and taking the symmetric multiplication, we actually get a map from Sn n plus I to V. We actually started with a map from Sn to V, and we ended up with a multiplication of Sn plus I to V. And this is an element in pi n plus I of V, which we will call the steenrod operation SQI of X. And why are these steenrod operations very useful? Because while in the by taking the cohomology is commutative, but on the level of cochains, it's not actually commutative, but it has a symmetric multiplication. So while going down to the level of cohomology, we actually lose structure. So these steenrod operations are actually used to have that structure. It carries that structure because it's defined with symmetric multiplication. And actually, in order to construct all the data of the cochains, we actually need to have only the data of a cohomology and some different and more sophisticated version of the steenrod operations, which was proved very recently. Yeah.